Good afternoon, everyone. Welcome to the EWRC seminar. This is also the energy seminar, and we have them collocated today. We are very lucky today to have the external speaker, Professor Bassam Dali, from King Abdullah University of Science and Technology in Saudi Arabia. Professor Bali is a well-known expert in all energy subjects, especially thermal energy and combustion. He has done work in solar thermal, hydrogen, and he is also very well known for his work in fundamental research in energy using laser techniques, and he has now a very impressive record of achievements in this field. I know Professor Dali for already several years personally because I met him first in Australia, 2013. We were both working within the Australian Solar Thermal Research Initiative. I joined a year later after the initiative started. And we both moved from Australia, Professor Dali after some 20 or 22 years, me after 10 years. He is now a faculty member in mechanical engineering there and a member of the Clean Energy and Combustion Technology Center at KAUST. And today he is talking about renewable energy technologies and its applications in power generation and industrial process heat. We are going to see many overlapping interests with what we do here actually at the Cyprus Institute. So we are very happy to have you here, Bassam, today. And please join me in welcoming Professor Dali for this seminar.
Well, good afternoon all, and thank you, Wojciech, for the nice introductions. I'm really pleased to be here. It is accidental almost. I'm here on holidays, and I thought I have to stop by and have a look. So I'm glad it worked out. So thank you for allowing me to speak and for inviting me to be here. Let me just say a few words about the university. King Abdullah University of Science and Technology was established in 2009. It is a private university that is incorporated in the US. It's a global university, so our teaching is in English. We have students from 69 different countries. 50% of our students are international and 50% are Saudis. 37% of our students are females, and we are a science and technology university. We are very proud of what we were able to achieve. We have the very proud record of publishing more papers per academic than anywhere else in the world. There's 255 faculties in there and 1,600 students, all postgraduates, masters and PhDs. And we have our own board, our own management system, so we don't belong to the government as such, although we are a Saudi university after all. It's quite a unique experiment if you want. We do have our own funding, and we have our own labs, and we run our own campus. In the campus, there's almost 9,000 people live inside the walls. So it is a sort of a controlled environment, if you want. And a funny fact about it, we have, it's family friendly, so we have more school students than university students. Around 2,200 students, students come to the school rather than to the university because we accommodate everybody coming in and so on. So this is where I come from. The center that I belong to is CCRC, and it's a Clean Combustion Research Center. We're evolving sort of into Clean Energy Research Center. So I established Renewable and Sustainable Energy Technologies as part of the center, and this is where most of the work has been done. So the topic, it's synergetic renewable technologies. I wanted to show that because renewables are intermittent, because renewables are expensive, because I'm really interested in decarbonizing not just the power but the industry, then having hybridizations and synergies will make things a little bit more palatable, at least in the transition period. Nobody know how long this transition is likely to be, but at least in the interim, we need these technologies that capitalize on this and that in order to actually get us where we need to go in the short term. So I have to start by acknowledging all the people who sort of helped me achieve all of this, students, collaborators, postdocs and so on, as well as the funding bodies. Some of this work started back in Adelaide, where I spent 22 years, and then continued here at CAST. That's my group, although we're missing a few people. Some moved on already. We have 17 in my group, and they're really working hard, and I'm proud of them. And I have quite a broad range of interests, which I'll talk to you a little bit more about. So this is what I do, and in fact, I was asked to write a 3-year report sort of as part of my employment, and by the time I listed everything to you, it scared me that I have such a broad. But this is the nature of the beast, is that if we focus too much these days, we're missing the big picture. And hence, I think Wojcik's description that I look at lots of anything thermal in a way is quite accurate in a way. So concentrated solar and for power and industry is, so basically maybe I'll go to the next slide, the next thing. So these 3 things I'll talk about today. Out of everything else I do. But Wojcik said make your talk a little bit more broad, so we could have a, because this is my first sort of, to cast the net much broader, and then we'll see we could focus more on our discussions on things that are of mutual interest. So I won't discuss much about the 3 that are in blue, in the sort of highlighted in yellow. But the plastic recycling, supercritical water gasification is something I got interested in. I got funding from the university to basically take this plastic and produce other syngas or hydrogen. At these temperatures of supercritical, the reaction proceeds at really fast rate, and as well all the impurities goes to their absolute elements. So what we have in here is gaseous products that basically is either water, CO2, or hydrogen, or CO, and then everything else is basically becomes inert. Hydrogen production via gasification of municipal waste and so on, that's another project that I'm interested in. That's sort of also looking at how do we produce hydrogen from that. And then steam calcination of CO2. So we looked at, this started in Australia, is that most of the problems, for example, and I'm interested in cement, most of the problem is you take limestone, which is, calcium carbonate, and then you remove the CO2. 60% of your carbon, or CO2, comes from the cement, but the other 40%, or thereabout, comes from the combustion to heat it up to the required temperatures to do the calcination. So the concept came that if I use steam instead of combustion products, can I then have steam and CO2 in the exhaust? I could condense the steam and then collect the CO2. So this way, most of the problem with CO2 collection, as you know, is separating nitrogen and CO2. If I only have steam, then I could capture the CO2 at a relatively low cost. It turns out also that steam does have some catalytic effect, yet to be fully determined. So our project looking at how does steam impact on calcination for different ores, in fact. And we're finding that there's really interesting results. In one instance, for example, for magnesium carbonate, we were able to reduce the calcination temperature by 200 degrees. Now, of course, you'd come to me and say, how are you going to produce steam at 800 degrees and so on? This is where sort of there's another innovations that we're looking at. The idea is that the whole process will be driven by renewable energy. Imagine you have a kilogram or liter of water. You put it through an electrolyzer, which is roughly 70% efficient. You're splitting it into hydrogen and oxygen. And what you do is you re-react it again. And you react it, of course, if hydrogen and oxygen burns, it's going to give you 3,000 degrees. But if you put more steam with it, or more water in it, you're going to basically dial the temperature of steam that you require inside the combustor at pressure if you want. Some of these electrolyzers can give you up to 30 bars. Now I have a steam at pressure, at temperature, that I can sort of utilize for these processes. And it's all powered by renewable electricity, because this is where I start the splitting process, yeah? We've done a little calculations about the energy balance, about the cost, and so on. It seems that it's actually really viable. Question is, of course, there's material issues to resolve. There's other issues. The good thing is I don't need the hydrogen to be high purity. I don't mind if, the conversion efficiency is not that high, because I'm going to inject more water later on anyway. And if I'm separating the oxygen and hydrogen, then I'm reducing the risk of combustion, but I then introduce it later on into the combustor. So this is my interests and expertise in combustion and my knowledge of some of the renewables sort of combined together to give me some synergies between this and that, okay? Ocean thermal energy conversion, this is just a small project I looked at. Where can I convert the difference in temperature within the ocean to generate basically power in remote islands that give you base load, and can then combine it with other renewables as part of the synergy to actually then continue operating. So Saudi Arabia is looking at developing these islands in the Red Sea, and they want to make them resort islands which are sort of green and so on. So this is part of a technology that does not take a lot of space, does not require lots of PV or mirrors, but can then utilize the temperature differential. Unfortunately, although the temperature of the water in the Red Sea, it can reach up to 35 degrees, because it can be really hot in summer, below sort of the temperature below up to 200 meters, it stays around 21. So delta T is not big enough for it to be viable. It does have its own sort of advantages, but this idea of having some sort of combination of base load and renewables also is relevant. Adaptation of hydrogen and ammonia to industry, so this takes me back to my combustion sort of background. One idea, when you burn hydrogen, there's no, the radiation is reduced by almost 90%. Because most of the thermal radiation comes from the CO2. Then if you don't have soot particulates, anything that radiates energy out, you only have the water vapor, then the thermal radiation from the flame is low, the volume of the flame is low, and then your thermal efficiency drops. So I was looking at, can I inject aromatics, even biomass aromatics, with the hydrogen, to generate soot within the flame envelope, which radiate my energy out, okay? And then burn it before it gets to the exhaust. So I may end up with 1 or 2% CO2, which is coming from biomass sources, but I increased my efficiency by 30, 45, 50%. So that's another project that actually is funded, and we're looking into how do I make hydrogen more adaptable to existing systems. I have a project with Aramco. They're saying, well, we don't have much bio-oil in Saudi Arabia. Can you inject naphtha with it? As long as it's 1 or 2%, I could then adapt a hydrogen burner to an existing boiler and then use it this way. The last one is the Future Cement Consortium. So I was able to convince all cement companies in Saudi Arabia and the ministry to come to a consortium and to basically develop, through research and development, also the pathway or the roadmap to decarbonizing cement in Saudi Arabia. And that's going to basically bring also other partners, and then cement is a major problem. So this is in general what I do. There's a lot of smaller projects that I won't mention here. Okay, so let's look at CST, and I'm sure a lot of people have interest in here. And apologies that I kept it simplistic, and some of it is straightforward, but I didn't know how broad the audience knowledge is here or online. So I don't have to dwell on this. How do you concentrate solar energy? And I'm sure all of you have seen this before. The size of the solar resource in here is, of course, they will power the rest of the world. But this thing, as most of you would have seen as well, and you could see here how the cost of CSP has been dropping much faster than the PV ever did. And although I only have data at 21, I think the trend is continuing, especially that China is coming online now with massive automation of the production, and where their pilot plan is 110 megawatt. So same thing happened. There's an interesting video online. I encourage you to watch it, by Martin Green from University of New South Wales, where he talks about how PV reached where it is. And he says how his Chinese PhD student, who they have a patent and a new invention, went to China, raised some funds from the government, and then started manufacturing PV cells, how he listed in a stock exchange in New York, how within a week he raised $100 million, And then he goes through this process of how the PV cost actually have been reducing over time, and how sort of they reach some plateaus at some stages. And he says, okay, now scaling is not enough, we need innovation. So when innovation comes, then the efficiency increases and so on. But you could see somehow we are reaching sort of some limit in terms of how much additional. Of course, the more penetration there is, there's a problem with storage. Batteries, I'm sure you've seen the critical minerals report, how sort of lithium, they're saying by 2035, I think, the demand for lithium is going to be twice the ever possible supply, and only in 22 alone, the price of lithium went up twice. So there is a problem in terms of storage, and where CSP, of course, offers a lot of advantage. So you could see in here the LCOE have been dropping. I mean, it's all captured in here. And the other two is wind, of course, that you could see in there. And this is what's relevant to us in there. This is Saudi Arabia, and this is the solar resource in Saudi Arabia. I'm sure you've heard about NEOM, the new city that being built in there. NEOM is going to be here in this area. And you could see here you have the best results. In fact, if a combination of solar and wind could give you roughly 19 hours. Now, that's really a lot of energy that you could utilize. So what this shows is how the relevance or the relative amount of energy available to Spain, where sort of Spain was one of the pioneering countries to install sort of renewables. And I'll put in here Dubai, because as you know, Dubai is just commissioned 250 megawatt of tower plus troughs as well as part of their energy mix. Interesting, I was talking to Aquapower, who did the project in there, and they're saying that our initial contract that they want us our energy to kick in at 4 p.m. until the morning. And of course, that's all about storage, because I think they have something like 18 hours of storage or thereabout. So, but then they change the contract and they supply sort of energy across the day as well. Cyprus is here, I understand, correct me if I'm wrong, around 2,500, 2,600, and think in certain areas. And this is where Saudi Arabia is, of course. It's not as good as Morocco, but or Chile, but I mean, it's quite respectable in that regard. So this motivates us to sort of look into this as an opportunity to do concentrated solar. One of our problems that we have with Saudi Arabia is a lot of sand in the air that comes mostly from Africa. So these wind streams come in. The good thing is that this problem is only here, not here. And so the DNI at that area is actually quite good, and then we are able to sort of utilize it. And I think storage at the end of the day, where CSP thermal storage is, of course, is an advantage, and that can be utilized and can reduces the cost if you combine them together. And this is an important statement, saying that there's more CSP thermal storage connected to the grid than battery storage. I mean, I think only three plus years ago, there was the biggest Tesla battery in South Australia, where I was, in the University of Adelaide, of 100 megawatt, but that would run the state for 1 hour only. They installed it for a different sort of reasons, the way they wanted to stabilize the network, and as well as they wanted to break the monopoly of two companies in there who were sort of holding supply to get the prices up. They recovered the cost within 2.5 years, which is substantial, you know. So again, this audience would know all about it, but capacity factors. This is another plot showing sort of the thermal storage as compared to all scenarios associated with batteries. Now, of course, some of you will jump at me and saying battery technology is being developing, you know, and every second day there's this big announcement. One thing is to have something really efficient, another is to have it at cost effective, as well as a supply chain. These days, people talk about TRL 11, not just 9. 9, it's commercially available, you buy it off the shelf. 11, can you buy, is there enough of this material? Can we produce it on time? Can you install it? I mean, taking it to the real world is different from saying, okay, I could buy it today. Sure, demonstration is all over the place. So problem is, can we actually make it happen? And would it make any impact or difference? Again, here, sort of, comparisons between costs of storage of different types and how the distribution is in terms of the capex. I mean, I started by talking about synergies, and in here you could, again, this will not be news to you, is that the levelized cost of electricity when you combine CST and PV is much better than you have PV and batteries. And so this is where I think the niche markets for CSP needs to be. In addition, in my opinion, its applications to process industry and to industry. There, our efficiency is almost 80%. Okay, whatever losses you have in the system, you're collecting all this thermal energy that you could utilize directly rather than sort of convert it through cycles and so on. And here, sort of the different molten salts and so on that you could utilize. Its cost, of course, going into high temperature will give you higher efficiency, of course. So in that, his small projects we did, a master student was visiting me. I'm not sure if you heard about concentrated PV and thermal, CPVT. So what you do, you use a Fresnel system. You put here a channel that has some sort of liquid in it, and this liquid has nanoparticles that can absorb at a particular wavelength. One of the problems with PV is that you only utilize the visible and the UV, and all the infrared is actually where the heat is, and that's basically heating up the cells and making it less effective. Of course, in Saudi Arabia, it gets up to 50 degrees, so the temperature heats up, so that you can't cool it down, and then the efficiencies start dropping after a particular sort of temperature. So the idea in here that the energy that you collect, mostly in the long wavelength, that you store, and we kept it atmospheric and 95 degrees, and then you could utilize, of course, at low efficiency, but you have some sort of storage and then the rest of it will go into the PV, you know. So we done, I mean, it's an exercise of looking what the techno-economics would look like, monofacial, bifacial, at different places in Saudi Arabia and so on. It's expensive, yeah? But nonetheless, I mean, we need to keep thinking outside the box. We need to think how can we, you know, solve this problem. The thing started is PVs are, performance starts dropping when the temperature is 50 degrees. What can I do about it? I could have PCM material on the bottom and try and cool it down. I could have a more elaborate system, or I could collect this energy and do something with it. Currently, it's, of course, it's too expensive. Now, looking at next generation in a way, one thing I got interested in is supercritical CO2 cycles. If I could get to 700 degrees, the good thing about supercritical CO2 cycles is that you could operate at a higher efficiency at low capacity. That means a 1 megawatt turbine, which usually, you know, you fit in a table, of course, have a really good efficiency. And with these concentrated solar systems, you're not going to go to 100 megawatt if you have a cavity and high temperature. You're going to be restricted to, what, 10, 5, 15, I mean, 30 people say. So then you need a energy conversion cycle that is high efficiency at low capacity. So we start looking at, I mean, we're not the only one, of course. There's a whole European project looking at supercritical CO2. And then can we do supercritical CO2 cycle using solar thermal and what we could do about it. And then in particular, we focused on the receiver. So this thing was designed and being built. So the idea in here is that first, this heat exchanger can handle 100 bar. It's 3D printed, and it has special sort of channels inside as well. The volume is full of molten metal. Currently, we're using gallium. And you have a normal sort of cavity in here. And the idea is I could run it to 100 bars, 700 degrees, which will be highly suitable for supercritical CO2 applications. For CO2, you need 70 point something, I think, 70.1 bar to get it to the supercritical conditions. and 700, of course, is good. So what we're hoping for, and why we actually then filling it up with molten metal, is to enhance, of course, the heat transfer, and to allow this heat exchangers to expand in whichever way it wants without being restricted, other than sort of on the top in here. Of course, there's another inlet as well. And then have basically almost some thermal mass that if I have a cloud or something like that, then I don't end up with sort of total reduction in a very short period. So this work is started with University of Adelaide. Mehdi Jafarian, who's now moved on to somewhere else, sort of is supporting us. And it's no news to you is that the receiver's timeline is measured by the number of cycles, yeah? How many times you cycle it up and down and so on. So within this sort of, we could keep it hot for the whole night, hopefully, and then continue operating at relatively high temperatures and pressure, of course. So for that, I did build a solar simulator. It's 42 kilowatt electric, giving me around 12 kilowatt thermal. Bought it from China, give me a 60 to 80 millimeter diameter, and it can be modulated from 2 all the way to 42. 7 xenon arc lamps, and each is 6. It's now fully operational. It took us a long time. It's a small room. You need to get all this in it. The rest of the 30 kilowatt you need to get out somehow, which we managed to do that, and then now it's fully operational. So that's one reactor, which I'll talk about in a minute, which sort of is involved in creating what we call complete hydrogen, which I'll talk about. Anyway, it's not new in here other than the other systems that we operate. Oh, here's another design which is sort of, again, utilizing 3D printing. And here I want to do sort of industrial gases. I want to heat up air to high temperature at pressure and see if I could crack sort of the, I guess, efficiency part to try and make it sort of economical. So what you're looking at in here is a 3D printed porous material made out of Inconel in this case. And within it is a double helical integrated heat exchanger that will give me up to 10 bar for now. Now, we set 10 bar to allow it to go, but I think we're going to do hydrostatic testing to see if we could go to much higher pressures. Idea in here, we modeled the whole sort of system. We do have a concentrator in there. And then we looked at sort of the flux at different directions, and then we changed the porosity to trap the energy as it goes through. And then we've done some modeling, and we think it's going to work good. It has been printed. It has been heat treated. We should get it next week. And we sort of want to try and start with air and see how we go from there in terms of other gases that we were going to try and basically pressurize and heat up and see what sort of, mostly we're interested in the sort of energy density evaluation. Can I get to the energy density required to make it viable, basically? Of course, building anything from Inconel is not economically viable. It's perhaps the most expensive piece of metal I built. But still, I think it's the principle of it. If it works, then we could look at other ways we have to do it. Putting steam in, that's a different story, but we something that we're thinking about in the future. That's another project looking at, I mean, this is a simplistic view. Can I use concentrated solar for ammonia cracking? Of course, 28% of energy of ammonia goes to power the cracking back into hydrogen and nitrogen. The idea is that Saudi Arabia wants to export blue ammonia to the world, and then from there on, they're going to crack it. They develop a very efficient catalyst, but they need to run it at 450 degrees. So the idea is, can I do this here? And can I heat it up 450 degrees and so on? And what sort of conversion efficiency I'm likely to expect? The catalyst is supposed to operate at more than 80% at these conditions. Of course, you need the membrane, you have to separate it and so on. But the real big project is looking at hydrogen sulfide. Most natural gas in Saudi Arabia has H2S in it. And there's a lot of restrictions. Once it burns, of course, it creates lots of nasty things that you don't want in the atmosphere. Then they're looking at what's called a photocatalytic way to remove H2S. Currently, they're saying, just destroy it. In other words, there is a catalyst that could operate up to 800 degrees, by which H2S is basically separated. The sulfur is supposedly end up in its solid form that we'll be able to remove, and then you have hydrogen that goes with the natural gas we don't want to capture, basically. So this is a real project with Aramco. First to try it and with a simulator, and they allocated a few $1 million to actually build and test. So that will be quite an interesting thing to take it to the real world in the next few years. That's another thing that I learned in the past, and also with the synergy, is hybridization. So when we looked at how do you introduce renewables to industry, first thing industry wants firm supply. They want it all the time. They want fixed temperature. And then, okay, they want certainty. They're risk averse. They won't sort of allow you to come, oops, today the sun is not up and so on. So what we came up with is what we call a hybrid solar receiver combustor, basically, again, combining both expertise. So this is just a normal cavity, basically, and here we have additional burners that during the night, we are able to close this window in here and operate the burners, basically keep the whole system hot, and then during the day, open it up and continue operating. But what we managed to do is also do what we call 3-mode, is that solar only, combustion only, and combined solar and combustion. And we built the system at 20 kilowatt, could go up to 40. And then we looked at sort of the efficiency of the collections, the maximum temperature we are able to achieve. And then we had students doing techno-economics as well. So, I mean, there's advantages, of course. You could start operating anytime, sort of once the sun is up. So you don't need a threshold for things to start. You could sort of continue operating, so your molten salt remains at the required temperature all the time. It's one system rather than 2 or 3, sort of you have one basically energy source if you want. So we compare this to a standalone boiler and so on that it needs to run idle all the time and so on. So this is sort of continuously operating. And as you could see in here, we operated the system on hydrogen and CO, on hydrogen alone, on methane, on propane. So we were able to actually make the system work. And we also used a lamp at the time to sort of put the solar system in. Since then, we moved in what we call sort of generation 2. Instead of using convective heating, as you could see in here, we actually then replaced these normal burners with radiant burners. And then say, okay, if I want to use only radiation, which what the solar is giving me, I could then have these burners actually radiating energy in a similar way, and then I'll be able then to operate, in fact, more efficient, reduce then the length to diameter ratio to 1, and then I'll be able to build a system that is efficient and can sustain itself. So I'm looking to scale this up. It's not on the top of my priority. We do have a sort of provisional patent on it, but that's something in the background now. So let me summarize the concentrated. A variety of projects that capitalize on the Kingdom of Saudi Arabia's advantages and synergies between new and existing technologies. Interest in scaling up technologies for the supercritical, for industrial applications, for the hybrid, and also for the ammonia and sulfide crackers. I could stop here, or basically, we'll have questions at the end, yeah? Okay. Another interest of mine is H2O2 as oxygen carrier. If all goes well, we're going to produce 500 million ton of hydrogen by 2050. For those 500 million ton, we're going to produce something like 4.4 or thereabout ton of oxygen. Now, what do we do with this oxygen? And this is what got me interested in H2O2. So this is the motivation, is they finding sort of cost-effective solution to store, transport, and utilize oxygen, and will help reduce the cost of. If I can valorize oxygen, then the price of hydrogen is supposed to drop from green hydrogen. So the concept is to convert or to store O2 in H2O2. And I'm going to end up with 40+% by mass of H2O2 being oxygen, basically. So using rather electrolysis, plasma, and then transported with hydrogen. Now, H2O2 in its pure form is highly explosive. It has been used in the past as a rocket fuel. But if you blend it up to 40% H2O2 in water, it's safe. You could you go to the shop and buy a gallon, bring it home, yeah? And find utilization routes. So one thing is to produce it. It's another thing, what do you do with it? I mean, one of the questions people are asking, okay, we have oxygen, but all the oxygen we need, we could do air separation unit and generate it on the spot. You don't need any of this. Of course, there's a cost of transport, a cost of pressurizing, and so on, and risk as well. So what we wanted to do is to generate green H2O2. In other words, what I wanted to do is I want to oxidize water with oxygen to produce H2O2 using renewable electricity. This way then, in fact, each H2O2 is storing some energy in it, and that's renewable. So I'm not only carrying oxygen, I'm carrying also renewable energy. The second thing, I'm going to use it to capture CO2. Now, what we figured out, that H2O2 is an oxidant, even at 40% in water. I'll show you some flames running with H2O2 as an oxidant. So now, what I have in the exhaust, again, I have water and CO2. I condense the water, end up with CO2. So that reduces the capture cost. And maybe also use it for blue hydrogen. What do I need to produce hydrogen from fossil fuels? I need steam and I need oxygen. Now, this has steam and oxygen and energy, renewable energy in it as well. So this is the concept, yeah? This is a little bit more information about H2O2. I won't bore you with a lot of the details. It's an interesting molecule that can easily lose its oxygen if it gets in contact with some metals. So you need maintaining it at its sort of original form is a challenge. But if you put it in water, you should be safe. So usage and price, currently there's 4.5 million tons per annum, 2020. Paper industry, chemical synthesis is where it's used. Market price between 500 and 1,200. Remember these numbers because I'm going to show you new numbers in a minute using the other routes, basically. So this is how it's being used. Disinfectant, by the way, you could buy it in the pharmacies, or people use it to clean things, but they're a concentration 1 or 2%, basically. So grades, 90 to 95% is pure fuel in rocket propellants. 35% is for other things, and less than that for domestic use. Okay? So there's a market. We know how to deal with it. We are producing it for a while. This is where it's being produced. Again, I won't bore you with the details, but this is where most of the production is. And then the large scale is using an agent, which is what's called an anthraconium, where basically 95% of global H2O2 being produced today. The most important part about this is through doing this, of course, you have to start with the hydrogen and the oxygen, and then combine them using a third agent, and then, it's a lengthy process. It's actually energy intensive. And each ton produces roughly 600 kilograms of CO2. So, yes, I want to valorize oxygen, but if I'm able to find a route to produce H2O2, green H2O2, then I actually also saved in CO2, and then I'll have new market for it, although the quantities are not huge. The other process is oxidation of alcohols, direct synthesis, electrochemically, and then plasma and water. So I'll show you some of these techniques and what's wrong and what's good for it. So here's the three. So there's hydrogenation, there's then oxidation, and then extraction. And then this is the magical number, 600 kilograms of CO2 per ton of H2O2 today. And it's energy intensive as well. Two propanol oxidations or other oxidations of alcohol is also unknown, but you have to start with something that is already sort of be produced. Of course, that comes with a cost and so on. Direct synthesis, hydrogen and oxygen, but the idea is to valorize oxygen from the green hydrogen industry. I don't want to utilize this expensive hydrogen. I want to basically have different ways to actually produce H2O2 rather than utilize hydrogen itself. So electrochemical, I mean, it's a known process. The problem with this is that it's not its stable form. It does combine, but it can easily sort of go back. Maintaining it at its current form is actually one of the problems. So having selective sort of catalysts, having the right environment, has proven actually to be quite generous. So actually, this is the route I took first. And I had a postdoc, spent 6 months scanning the literature, trying to do things himself and so on. And the best we found is a paper which claims 10% H2O2 using electrochemistry. And then we invited this guy to give us a talk and so on, and he said, okay, we're going to work with you. And it turns out the whole thing is a hoax, basically. He won't tell us what he did and why he did it, and that he'll be able to reproduce it. And then I spoke to an expert in the field, and I say, don't believe any catalysts. I'm sorry if there's any catalysts here. They're saying that most of them produce material that, okay, and happy to put it through the market and to be tested, but there's lots of claims in the literature that cannot be reproduced. Now, anyway, it is a problem. It's that it's not easily done. You need expensive materials to be able to do it. And then so I gave up on electrolysis or electrochemical sort of ways. And then I went to plasma. Now, producing ozone with plasma is a well-known thing, okay? There's a lot of work that's done with air. The problem with air is that you have oxygen, you have nitrogen, and you have high temperature, you're going to end up with NOx, NO and NO2. And we're creating a new problem, okay? And this oxygen is going away to produce NO and NO2 rather than to produce sort of H2O2. So oxygen alone in plasma with water have two routes. One is with H2O2, it can actually produce OH and H. And then oxygen alone can also produce ozone and O. So these two can combine and produce another OH, and then H2O2 is two OHs together. Now, the problem is that it can also combine and reattach itself. So this is where we're up to now. Very little research of oxygen and plasma. I have a program just started we have an expert in plasma at KAUST, Diana Lacoste, and we decided to sort of start this project of trying to, we're not the first ones to basically put oxygen plasma in water, but nobody had an intention of increasing the concentration and what do you need to do on pressure, temperature, and do you need a third agent to scavenge it, basically what's being produced. So this is where actually all of our research is happening in here to try and increase the yield and monitor the amount of energy being utilized. My current thinking is that energy efficiency, of course, going from electrical to plasma has its problems, of course, but the energy is all inside the water solution that I'm trying to produce. The question is, how do I convert it to right sort of chemicals that are required rather than into just thermal energy? Now, utilization, I said to you that there's only 4.5 million ton per year. It's not a lot in terms of consumption. So we came up with this concept. If I take a fossil fuel and react it with H2O2, we're going to end up with CO2 and water. Not just that, you know, when H2O2 dissociates, it gives me this energy. Now, this energy came from renewables. Okay, so I'm not only carrying oxygen, I'm carrying also renewable energy with me in the same molecule. So here's a flame that is running with, this is with hot air, this is with nitrogen, and then this is with this sort of H2O2, which is, I'm not sure which one is, but what we did is we put oxygen and steam, and then we put H2O2, and then we compared the energy that has gone away within that. So basically we found that if we raise the temperature to 130 degrees, that's enough to vaporize both water and H2O2, and then 40, 60, then we have a sort of a stable flame that we are able then to utilize, and then if we condense our water, we could be able to capture the CO2. Now, this actually started well before. This started in Adelaide. We have a provisional patent, and it says, can I use H2O2 for limestone calcination? And it's the same concept again, that bringing in some fuel, then I'll be able to capture the CO2, and then basically I don't have any nitrogen in the system at all. Then we've done some techno-economics and looking at how much it would cost and at what price. This is the energy from CH4 air. This is the basically temperature, flame temperature from a mix of H2O2. HP is hydrogen peroxide, and methane. You could see, depending on the concentration, we could achieve higher temperatures than we have in here. So temperature required for calcination can be achieved through the system. And then we looked at how much the CO2 saving is. This is if HPE, or the hydrogen peroxide, is produced from the current process. That means 600 kilograms per ton. And you could see in here that we are able to save up to 40% in CO2. This is if it's produced from renewables. So we have a major, basically, whatever we are saving. In here, of course, you'd ask, why is it positive? Mostly because, you know, we haven't spent the 600 kilograms in the first place. So the other approach is, you remember I said that to reform methane, you need steam and oxygen. Well, H2O2 gives me both steam and oxygen. So the idea in here, can I react my fuel, whatever it is, with some H2O2, of course there's water around, and produce sort of my hydrogen, and it's roughly, it's energy neutral. And then so we've done some work on this, and we believe that it's actually doable. That's the student now is experimenting on it, and that will give an advantage. Why? Because then this stream of H2O2 I'm producing has direct application. And, you know, we are talking about synergies. It is a product of green hydrogen that's helping produce blue hydrogen. So one is complementary to another. So then, of course, the big question is, this is too expensive, this is stupid. I mean, how can you make it work? So we went to compare what do you do with oxygen with and without. And of course, we didn't go all the way to, okay, how much does it cost to capture CO2 as compared to sort of doing it this way. But here, sort of, we looked at Saudi Arabia and we said, okay, what if the H2O2 is going to be used in the Eastern Province? And the Eastern Province, basically where the Persian Gulf is, this is where most of the oil and gas resources are. This is where they're producing all their hydrogen. So the idea, and I showed you where Tabuk is in Neom, and this is where all the good renewable energy is. So we wanted sort of, do we use it in the western side of the country or in the eastern side of the country? So then we looked at different scenarios. I won't bore you a lot of the details. But then sort of we assumed that we'll be able to produce it from renewable sources. And then we compared producing it on the spot using ASU or basically transporting it over. And then here, if we want it in the Eastern Province, that means we're going to crisscross the country. And then there's two ways around it, basically either through a private pipeline or land freight. And then we're looking at the cost. Here, the cost is 1,480. Remember before it says between 500 and 1,200. So this is more expensive. This is also very expensive as well. And by the way, these are just transporting oxygen, not H2O2. This is basically compressing the oxygen, putting it in trucks and taking it to the other side of the country. And then we even looked at sea freight, and then we'll see actually it's relatively okay. And then transporting H2O2, and you could see the prices here dropped substantially, 484. So this is less than $500, and so on. And this is a comparison with an ASU unit, showing that if we do this, what do we get in return? And with the ASU, then you could valorize the liquid nitrogen. But then again, we'll end up with the same problem. We have too much nitrogen, which may not be needed, or it's in the wrong place. Anyway, it's just an interesting exercise of if it becomes viable, or if it actually will solve all the technical problems, would it be viable financially? So here's a summary of this. So we developed plasma system for O2 and H2O to produce green hydrogen. Developed scaled up technology for utilizing of H2O, H2O mixture, and the capture of CO2 from fossil fuels. Scale up autothermal methane reforming using that. And again, investigating hydrogen peroxide for the calcinations of limestone manganese and bauxite. All of those are of interest to Saudi Arabia. So this is ongoing project. I have 2 postdocs and 3 students working on it, and have interest from industry as well. All right, my last topic is about turquoise hydrogen. Of course, many of you know all the different colors, and the black, gray, blue, and green. Ultimately, we're all going to do green because we love green, but at the end of the day, of course, we all know it's not going to happen. Issue was that 70 plus 80% of the cost is electricity cost. That requires PV currently. The prices of metals going through the roof, so the PV basically cost is now plateaued. And we have a problem of supply, and also these sovereignty issues. There's a lot of countries now hugging their own supplies and saying, China in particular, for example, a couple of months ago, says ban on export of any lithium extraction technology, full stop. They don't want anybody in the world to basically extract lithium because they want to take control of that market. 70% of batteries in the world are produced in China, as you know. And it goes on and on, of course. So it's not just about, can we produce it quick enough, but where we can produce it. Even Saudi Arabia now is buying mines in Chile and in Africa to secure some supply of special metals that it requires because they want to produce electric cars as well. So basically, these are the costs. As you see in here, currently, sort of from coal is 1.34. Then, of course, the price drops depending on where you end up in. So this is the CO2 emission in here, and this is the cost. So currently, it's anybody's guess what the number of what's the cost of green hydrogen is, but you could see that blue is at 1.34 and gray is at 1.9. So the idea, if you want to produce turquoise hydrogen, then it need to be competitive with that, and also in terms of CO2 emission. You know, we can't take one and ignore the other, yeah? So what is turquoise hydrogen? Basically, we're taking natural gas and we converting it into hydrogen and solid carbon. And the way you do that is different ways to do it, but what we're interested in is this sort of, sorry, I missed something here. What also encourages us is that the market for turquoise hydrogen is about to mushroom, and then the sort of compound growth rate, annual growth rate is likely to be by 2031, 144.6 billion. So this is big money if you can get it. The question is, would it add up? So again, red flags, high temperature requirement, gas phase pyrolysis, solid carbon deactivation, catalyzed pyrolysis, and hydrogen selectivity issues. So many of the other problems do have. There's commercial companies that are operating today. Some of them compromise the catalyst, like in Australia, the Hazer Group, they put iron particles in there. The iron particles capture the CO2, the carbon, and then they dispose of it. They pile it up, basically saying maybe in the future it will be worth recycling, but iron particles is relatively cheap. Others do other things with it, but this is where we're interested in molten catalyst pyrolysis, and also in the hope that we'll be able to solarize it as well. So we have some funding from Aquapower. This is how the process works. Basically, you have a molten catalyst. You simply bubble the things through it, okay? You collect the particles on the top, and you collect the gas in the exhaust. Advantages: reduction of temperature by 200 to 300 degrees, excellent heat transfer characteristics. There's some papers show that the heat convection coefficient is something like in the 10,000, 12,000. Unbelievable. And then high selectivity to hydrogen, no deactivation of catalyst by carbon, and no CO2 generated, of course, and all these are advantages. Carbon black graphite has market value, and so on. So this is what we did. Basically, here's a furnace. We heat it up. Okay, inside this tube, there's 8 centimeters of gallium. We put a perforated sort of quartz system underneath. we brought some methane into it, and we bubble it through. That's the only thing we've done. And then we collected the, you could see in here how hot it is, and this is all radiation, by the way. It's not, this part is not that hot. And then we're collecting sort of the samples into GC, and then we looked at the convergence rate. And we changed the temperatures from 600 to 900, and changed sort of the flow rates, residence time, and then the porous size. And this is what we found, is at 700, we have 14% convergence, but at 900, we have 82% convergence. This is quite a high convergence rate, actually. So we're pleased with that, and then we were looking also how to scale this up. And this is also the mass flow rate. Of course, if you reduce the residence time, your convergence rate is going to drop, but you could make the bed longer. You'll increase a little bit of further pressure drop, but it's not a big deal. And the 700 and 800, and then in this effect of the pore size, the smaller the bubbles, the better sort of volume to serves the volume ratio. And then, so what happens are these bubbles, the surrounds basically is providing all the heat. Inside the bubble, you're creating the hydrogen and CO, the hydrogen and the carbon. Now, it's something that's in my mind I'm really interested in. If the path to the end of the bed is long enough, can the hydrogen penetrate from the bubble, separate, and then you don't have to worry about equilibrium anymore. You remember at different temperatures you're going to get equilibrium. Convergence rate stops and you're going to go backwards, yeah? So if we are able to make this path longer, can I liberate the hydrogen because it's, you know, 8 times lighter than carbon? And of course, all of its flaws because the molten metal is quite hot, yeah? It's quite heavy as well. So this is what you saw in the video before. This we borrowed from the University of Adelaide. Basically, it's a simple cavity in here. The solar goes in, surrounded by molten metal. From the bottom, we inject the methane. On the top, we collect the hydrogen. Okay? So we run this system. Unfortunately, we had some trouble. There's no information about how corrosive gallium is above 400 degrees. Basically, it doesn't exist. It says it's a little bit corrosive at 400. But when we went to 700 degrees, I mean, within an hour, we had 3 holes on top of this stainless steel reactor, which is 5 millimeter thick. Absolutely unbelievable. So students came and said, I have a leak. And I said, can be. But when we opened it up, sure enough, there's 3 holes in the top. I mean, the molten metal ate the stainless steel. So now we build a new one with better material. We're going to try it again, of course. But then we don't have to use gallium. Gallium is a metal of convenience, available, although it's a little bit expensive. But bismuth nickel is actually just as good, much, much cheaper than gallium. Gallium is expensive. But we wanted something efficient to show that what we could get to, okay, high convergence and so on. So corrosion relatively low, below 500, but above that, no data was available, so we cooked the system. Yeah, this is what we saw before. Of course, this is without the insulation, so I'm not sure what insulation. So this is the new design, and we're hoping to have results in the next month or 2. It's just a proof of concept. We wanted to prove to the industry that using solar, we are able to generate, we are able to produce turquoise hydrogen. Of course, in most other systems, you could use electric heating, resistive heating, or a hybrid system as well, and that you could continue operating during the night. Well, I don't show in here, we have a new provisional patent, I'll come to this in a minute, which actually have a 3-core reactor at 40 bar, a cool mechanism to collect the carbon, and also a mechanism to integrate replacement of the bed from the outside. That's something sort of in the working as well, and we're hoping to get some funding from the Saudi government. We've done an interview last week. Now our technology is listed in the top 10 technologies, strategic technologies for the kingdom, and we passed stage 3. So fingers crossed some funding is going to come to scale up, and we're going to do a 1 ton per day facility based on what we learned so far, and then see how we go with it. So we've done some modeling as well to try and understand what the cost is, because at the end of the day, if we aren't able to compete, then what's the point? And this is why I started with a slide showing what the current prices of hydrogen is. Okay, so to start with, we sort of compared our results with what's in the literature to make sure that our convergence model and the temperature is actually accurate with what's available in the temperature, and we'll be able to sort of duplicate that quite well. We've done some fitting on our data that we generated ourselves and then compared with that as well. And then this is sort of the process. I won't bore you a lot with the details, but here we're using a nickel bismuth sort of at 1100 C. And then there is one of the problems with these systems is very small traces of the molten metal can be carried out with the carbon. Now, it could be minute amounts, but over time, of course, you could carry a lot. So then also the type of carbon that you generate is highly dependent on the temperature and the type of thermocatalyst you use, the material inside. And the prices of this carbon, actually we've just written a review paper around to be accepted. The prices of this carbon can change by a factor of 1,000 if you produce this type or you produce this type. If it's a really low grade, it has two applications. You could add it to concrete and cement, and actually it's quite useful. You could also put it to enhance a quality of soil. But if you go to the other end and you produce sort of carbon black and so on with a particular sort of phase structures, you could get 1,000 times more money for it. And so when we do our techno-economics, we don't assume it's going to be this. We assume it's going to be across the whole thing. In fact, in the current model I'm going to show you, we assume that there's no value for the carbon as such, just to be on the safe side and saying anything that the carbon add is a bonus rather than sort of is going to be an impediment. Again, this is a sophisticated model looking at what we could do with it, but as you see, the system is relatively simple. Of course, we need to do cleaning, we're going to recirculate things that haven't been converged and so on. Yeah? Techno-economics, again, this is all the details, and some of it is well developed, others is a little bit low TRL. But let me show you some results. So currently we're looking at powering it using electricity, and then we sort of have to assume what the cost of grid electricity is. And then also if we're doing it solar PV and storage, or sort of a mixed, we're taking both. And that during the day you use the solar and the night you use something else. Here also what we wanted to make sure of is that the lifetime of this nickel bismuth is that, are we going to replace it every year, or every 2 years, every 5 years, and then of course the cost will change as we go through. And then here sort of using this pressure separation, pressure swing sort of type system to separate the hydrogen instead of a membrane. And then we've done these comparisons, and here you see the hydrogen production cost per kilogram. And this is using sort of, currently the natural gas in Saudi Arabia is between $50 and $60 a ton. And remember before, the gray hydrogen was 0.9 and the blue hydrogen was 1.34. So we looking competitive with those. And you could see in here that we're looking at current sort of cost, but sort of production of hydrogen at the cost of gray hydrogen as a 0.9. You see this one here? And then, of course, zero CO2 in here because it's powered by renewable electricity and we're only producing carbon, there's no CO2. So there's a paper which you could look at, the economics of this, and you know how in Saudi Arabia it can be actually viable. Another thing we looked at is, can we use concentrated solar thermal to power the whole process instead of renewable electricity, and what advantages it will have. So we looked at the indirect heating with thermal storage or direct heating sort of system. And you know, this is a model, and then is it sitting up? Is it sitting down? How are we going to feed this? We haven't solved out the technical details, but it's just a model of coming and saying, if I use direct heat in, can I operate the system and would it be viable? So again, we built a model, ASPE model, looking at how much would it cost to have a parabolic dish, and would this dish sort of achieve the temperatures we require, and so on. And then compare this for 10 hours CST, 14 hours grid electricity, induction heating, 4.2 megawatt thermal. We're using gallium in this case, temperatures of 1100, methane conversions of 80%, and hydrogen output of this much, basically. And then when we've done that, again, the details are here. We arrived at this type of analysis, looking at the results for gallium. So bare erected pyrolysis and pyrolysis plus CST. And then I wanted to bring you to the cost. So here's the different cost of electricity. This is lifetime of the gallium being 2 years. This is 5 years. This is the nickel bismuth and so on. This is the blue hydrogen cost. And you could see what we actually, with gallium, we can be competitive if the price of electricity is $24 a megawatt hour. And if we're using nickel bismuth, although the conversions rate is a little bit less, but the cost of the catalyst is much less, and we are comparable sort of to gray hydrogen, well below blue hydrogen. Now, blue hydrogen cost, of course, predicated on finding a place to put the CO2. It's one thing to capture the CO2, the second is what do you do with it? Of course, with Aramco in the east, they put it underground and to enhance oil recovery. As the CTO of Aramco tells me, we get it out of the ground, we put it back in the ground. So for him, it's not a problem. In fact, you know, they're benefiting. They're reducing the viscosity, they're getting more oil out. But, and then there's, our university developed an atlas of storage capacity in Saudi Arabia, and we do have storage capacity for 10, 20, 30 years, but then from there on, what do you do? And of course, there's a lot of low TRL. We're not 100% sure it's going to stay there, and what happened to it, understood. Yeah. So combined CST is cheaper than pure electricity grid supply, and sort of, although nickel bismuth is slightly less active than gallium, but at low purchasing cost indicates overall, you know, it's better economics, of course. And then we're assuming conversion rate of 65, and this is how much we produce. So summary, combined concentrated is cheaper for pure electricity grid and power supply. Break even is 16 megawatt dollars per megawatt hour. Turquoise hydrogen at cost of gray hydrogen. Turquoise hydrogen at CO2 emission intensity of green hydrogen is possible. Carbon black is bonus. Anything I could get for the carbon is additional. No methane leakage during upstream and operation. So this is one of the criticism. If you start with methane, that your CO2 intensity will increase. And then hydrogen production can act as a bridging technology until green hydrogen catching up to $1 benchmark by 2050. So remember at the start of saying we're trying to find multiple synergies of using renewable energy to drive, you know, different things. And it's during the transition. And so this is where technologies would be required. Maybe in the future, green hydrogen is going to be the thing, but you know, there will always be plenty of methane around, and the transition will take a while. So these are my 5 remarks. The opportunity exists where synergetic technologies can be applied to reduce cost, provide firm supply, and enhance overall utilization. Scaling up is needed to de-risk some of these concepts. Current lab scale combined with advanced modeling can help in scaling and testing. And of course, we are open for collaboration in any of these and other projects that is of mutual interest. And with this, I'll stop and thank you for your attention.
And different energy technologies. We have time for questions. So, yes, Alaric.
Thank you, Professor, for the very interesting presentation. I wanted to know if you knew about the strategy of Saudi Arabia regarding the development of CSP in the coming years, decades, and also regarding the hydrogen technologies.
Sure. That's a valid question. So Saudi Arabia have two major policy announcements, one called Vision 2030 and one called the RDI, which is Research, Development, Innovation Priorities. It's basically what research and development required for the future. Within the 2030 vision, the only thing they say is that they want to reduce they want to switch the current production of power to 50% of it to be either from renewables or from natural gas. Currently, they are around 35% switching. So currently, they use heavy fuel oil, HFO, because it's cheap and they can use it. But as part of their plan to decarbonize, they want to do that. I have to say, out of the 35%, 1% is renewables, and the other part is natural gas. But they're building a big plant in NEOM as well, so PV and so on is developing and evolving. Out of this, as far as I understand, there's no plans for any CSP in the short term. Where CSP is going to come from, I understand, is in NEOM. NEOM, as you know, is a city, is going to have 2 million people. It's going to be the city of the future. And there, everything is going to be renewable. Everything is going to run in hydrogen. All their energy is going to come from renewable sources. And as we all know, they cannot do it on PV alone. So CST or CSP is going to be part of the solution. I'm having lots of discussions with them about energy storage, thermal energy storage in particular, and also about demonstrating, maybe sort of if I'm pushy enough, we will have a pilot scale facility at NEOM to basically demonstrate under their conditions different technologies that can be sort of use for the future. One of the reasons some of these slides I presented to Saudi Arabia companies is you tell them CSP and the first thing they say, it's too expensive and we have a lot of dust in there. Both are true in certain conditions, but one of the reasons I show the trend in coming and saying you're going to be missing out. Fact is that UAE actually have installed a big facility. In fact, the rest of the world is thinking about CST. And the fact is that the techno-economics is showing it's more feasible if you combine it with PV, is actually encouraging a lot of interests. So Aqua Power, one largest sort of power company, or renewable power company in Saudi Arabia, are lukewarm about it. They want to see numbers. They want to see where they can make money. And how they can combine it with their PV. So in the short term, no. In the long term, yes. I think it's inevitable in my assessment. There is a small plant here and there using troughs in combination with gas and so on, but it's not massive as compared to how much they produce. The second question was about hydrogen. So Aramco hedged its bets on blue hydrogen, in particular blue ammonia. But there's reports that I've read, not from Aramco itself, but sort of Financial Times and so on, saying that they're willing to invest billions to produce as much as the world needed. However, no orders yet. So is this a function of, Europe is in turmoil and the economy is not doing as well? Is it a function of, things are slowing down? I'm not sure. But they have the capability, they have the natural gas, they have the place to put the CO2. And in fact, they produced the first blue ammonia. And there's a demonstration thing. They sent a ship to Japan with 50 tons of blue ammonia, sort of 2-3 years ago, just for the PR of it, basically. There's even a talk about hydrogen pipeline to Europe, which is sort of a big dream for the future. I contributed a couple of chapters to a new book on hydrogen in Saudi Arabia. So if anybody is interested, it's available, it's free access. You could find a link for it in my LinkedIn profile. And it goes through the whole techno-economics, physical barriers, policy barriers, research and development. It's quite a big book, but there's lots of chapters, different contributors, and I have a couple of chapters in there looking at how hydrogen can be utilized, where would it go, and do they use it, do they import it, or export it, But transition is happening around the world, including in Saudi Arabia, where they see themselves as not an oil company anymore, Aramco in particular, but as an energy company, in whichever form it's going to come, basically.
Thank you. Some other questions? I have a question, Bassam. You mentioned hydrogen so many times here, and methane is one of the sources of hydrogen, but also water is used there, right? And Saudi Arabia is a dry area, dry country. So I know it was not the topic of your presentation, but what is the state of the art in basically provision of the process water to all this hydrogen production, ammonia, and where is it heading, if you can comment?
It is a very valid question and timely as well. So most of the desalination happens in the back of power generation. So they take energy from exhaust of gas turbines and do a lot of desalination. So power and desalination happen now as they're switching off these gas turbines, of course there has to be another source to power these desalinations. And of course they have a lot of reverse osmosis systems that they currently utilize, and water is an important thing for Saudi Arabia. It's one of their vulnerabilities. Basically almost only in few areas they have underground water. Most of it is actually desalinated. The good thing about Saudi Arabia, it's most of the population is concentrated in 3 different areas, so you could supply it relatively and they are, well, at least the east and the west are on sea, so you are able to get access to water. In terms of the hydrogen from water, it's not a big issue. It costs $1 to desalinate 1 cubic meter of water. So, in fact, sorry, even less. So, in terms of cost of the whole sort of hydrogen production, it's not a big cost. Of course, there's CO2 associated depending how you produce it, of course. So, they don't see it as an issue in terms of water supply to produce hydrogen. But as I said before, I think they're hedging the bets on blue hydrogen mostly. But along these lines, we're also looking at other feedstocks. Can I use naphtha? Can I use crude? Can I use RVO? So, VRO, I'm sorry. So there's a lot of other low-value hydrocarbons that we are able to convert using similar technology and produce hydrogen as well. So it's not an issue with water, and desalination will still be there in Saudi Arabia. One of the issues now they have to deal with is the environmental sort of authorities are coming and saying you cannot return brine to the sea. So that's another project looking at what do you do with the brine once you extract it. And some of the technologies of water, of steam calcinations being employed, looking at producing cement from magnesium. And, so that's a totally different topic, but it's sort of related directly to desalination.
Thank you very much. Is a question, Marius?
Basically, the question is a follow-up on what you just said, because if you get water to do hydrogen, now Saudi has this regulation about the brine, which they cannot throw brine back to the sea. So there is an opportunity there on how you actually treat the brine, and this could be also linked with the whole lithium and minerals extraction, which is something that, as you already mentioned, 70% comes from China. So I think it's a challenge and opportunity at the same time, because obviously I don't know how the hydrogen story will go and whether the water will come from diesel or not. By the way, $1 is quite expensive for us, at least, which is 60 cents.
I think it's less.
Yeah, okay. I'm just saying. So, I mean, maybe, yeah, it's a good opportunity now that you cannot reject the brine to look into that aspect as well.
It is suddenly a current project of extracting minerals from brine, because you already pumped it out, it's already on land. The question is, are the technologies cost effective enough? So we were approached by SWCC in saying, what metals can you extract, especially rare earth elements, because smaller quantities can basically make a lot of difference because they're really expensive. We found a couple. We looked at the existing technologies. We looked at some of our technologies, how to do it. It's still going to be, the concentration is so low. I mean, it's better than what's in the water, of course, but the concentration is so low that it's not yet viable. Although, in fact, I haven't talked about it, but we just bought an infrastructure, a process that can use supercritical CO2 with an agent to extract metals out of whatever system you have. And our interest is looking at circuit boards and electronic components and saying, can I target palladium? Can I target indium? Can I target gallium? And then extract it without needing to physically remove it as such. And the conditions at supercritical CO2 are conducive for this process to happen. Of course, you have to extract it after that. So that's another thing that's happening, and you could use it also for brine and may become sort of viable. But it is a hot topic, a part of what I called about RDI, Research, Development, and Innovation. They hired, I think, the Boston Consulting Group to develop quite a broad list of technologies and research that would be beneficial for the kingdom for the next 50 years. And then they introduced for sort of the first time in seriously research and development funds to accelerate these developments. And part of the funding we're looking for is coming from the government through this scheme. So, and it's available online, you could see it. Yeah.
Thank you. Do we have one final question from the audience? If not, then let's thank Professor Dali for this seminar. Thank you very much.
Thank you.